NASA detected a large hole that was expanding across the Sun's surface while analyzing its surface. Scientists predict that as a result of these changes in the Sun's atmosphere, a massive solar storm might erupt and hit Earth. The continual bombardment of charged particles from the newly discovered hole on the Sun's surface is to blame. So what dangers does this eerie hole pose to us? This is everything you need to know about this possibly deadly situation. Welcome to another video of Cosmos Observer, the only destination for your space curiosities. We will be analyzing the massive 75,000-mile hole in the Sun discovered by NASA. NASA claims to have discovered a massive hole in the Sun that is estimated to be 75,000 kilometers big. The space agency has given it the designation AR2665, and specialists have warned that it is huge enough to cause solar flares. Sunspots are colder patches on the star's surface created by interactions with its magnetic field. This particular sunspot is larger than the Earth, and researchers at NASA's Solar Dynamics Observatory, which detected the hole, said it was too early to anticipate how the sunspot would behave at this time. Despite its size, the spot is observable from Earth and can create flares that could result in radiation storms. Sunspots are prevalent on the Sun. However, they are less common during a solar minimum, which is a time of low solar activity throughout the Sun's 11-year cycle. The next solar minimum, according to NASA, will occur between 2019 and 2020. The Sun is by far the most important source of energy for life on Earth. About 4.6 billion years ago, the Sun rose from the gravitational collapse of matter within a region of a huge molecular cloud. The majority of this stuff gathered in the solar system's core, while the remainder smoothed out into the revolving disk. Nuclear fusion began in the core of the central mass when it became too hot and dense. It is thought that this process is responsible for the production of almost all the stars. The Sun is anticipated to grow large enough to engulf Mercury and Venus's current orbits, rendering Earth uninhabitable. However, there is no need to be alarmed because this will not occur for another 5 billion years unless the rate of reaction is accelerated. The Sun will eventually lose its outer layers and become a dense cooling star known as a white dwarf, which will cease to create energy through fusion. It may, however, continue to glow and exude heat. While in orbit around the Sun, NASA's Solar Dynamics Observatory got an astounding photograph of the Sun's massive surface hole. It was unprecedented according to observers. At its widest point, it has a diameter of over 50 times that of the Earth. A coronal hole is an astronomical event that happens in the corona of the Sun. A coronal hole is a sun hole that is not exactly a hole. In the plasma aura that surrounds the Sun, it is a much colder zone. In X-ray and extreme ultraviolet imaging, these patches appear black. Coronal holes are most abundant as the Sun approaches solar maximum, the most energetic phase of its 11-year activity cycle when sunspots and flares are at their most active. The hole is a low-energy, low-gas environment. As a result, certain magnetic fields fade away, resulting in reduced density plasma. The Sun's high-speed solar winds can then exit. When these particles collide with the Earth, geomagnetic storms ensue. When the solar wind collides with the magnetosphere of the Earth, the magnetic field of the solar wind interacts with the magnetic field of the Earth, resulting in an energy transfer. As a result, the aurora, one of the most beautiful natural phenomena on the planet, is formed. Geomagnetic storms can cause a variety of problems for humans on the planet. Particle activity in the magnetosphere can interfere with radio and radar communications, as well as GPS systems. Surprisingly, they also make it difficult for animals to travel. Homing pigeons, for example, have problems navigating during geomagnetic storms because the magnetic fields they rely upon as a guide are interrupted. On the beach, whales can congregate in large bunches. According to a project coordinator at NOAA's Space Weather Prediction Center, despite the astronomical activity in recent years, the Sun has shown modest movement. This occurs more frequently at solar minimum, as he points out. Nonetheless, we are rapidly approaching the solar maximum. That is, by 2025, storms will be even more severe. According to researchers, solar storms may cause the Earth's outer environment to overheat. Satellites, GPS mapping, cell phone transmissions, and satellite TV signals might all be affected. Power lines carry large currents that, if not correctly grounded, can cause circuits to explode. The Earth's magnetic field, on the other hand, serves as a protective shield. Explosions like these would be kept to a minimum as a result. Solar research is becoming more possible, allowing us to obtain a better grasp of the conditions that surround the Sun. There has never been a spacecraft that has come close to hitting the Sun before. NASA's Parker Solar Probe has completed its mission by collecting particles and analyzing magnetic fields in the Sun's upper atmosphere, or corona. The Parker Solar Probe was launched in 2018 to explore the Sun's mysteries by traveling closer to it than any spacecraft before it. It was designed to resist some of the solar system's worst circumstances. Unlike Earth, the Sun has no solid surface, but it does have a superheated atmosphere held together by gravity and magnetic forces. Gravitational forces and magnetic fields are insufficient to keep that material from being pushed away from the Sun by growing heat and pressure. The Alfvén critical surface signifies the end of the solar atmosphere and the beginning of the solar winds. As it moves across the solar system, solar material with enough energy to pass that limit drags the Sun's magnetic field behind it. Because the wind is flowing too fast, waves in the solar wind cannot return to the Sun above the Alfvén critical surface. The exact location of the Alfvén critical surface has puzzled scientists until recently. Remote scans of the corona calculated its distance from the Sun's surface to be between 10 and 20 solar radii, or 4.3 to 8.6 million miles. During its most recent missions, the Parker Solar Probe has been consistently at 20 solar radii, or 93% of the Earth's distance from the Sun, putting it in a position to breach the threshold. The Parker Solar Probe discovered a pseudo-streamer in the corona at a distance of just 14.97 solar radii from the Sun's surface. These ribbon-like structures can be observed rising above the Sun's surface during solar eclipses. Pseudo-streaming was like flying into the eye of the storm. When compared to the typical onslaught of particles the spacecraft confronts in the solar wind, particles slowed slower, and the number of switchbacks fell considerably in the pseudo-streamer. The spacecraft came across a location where magnetic fields were strong enough to block particle transport for the first time. Particles were sucked towards the Sun, indicating that the spacecraft had passed through the Alfvén critical surface and entered the solar atmosphere, where magnetic forces impact the escape of the wind. The mission's initial corona crossing, which lasted only a few hours, is the first of numerous planned Parker Solar Probe flybys that will come as near to the surface as 8.86 solar radii, 3.83 million miles during the next 4 years. It is an important subject to investigate because we believe a variety of physics could be involved. We should see some of these physics and behaviors in this area after a while. Unexpected physics is already surfacing. The Parker Solar Probe has acquired data revealing that switchbacks produce a continual and chaotic headwind of particles and magnetic fields flowing from the Sun as it approaches Earth during recent encounters. On the other hand, the solar wind is well organized and spotty as it leaves the Sun. The switchbacks were detected when the Parker Solar Probe approached 34 solar radii from the Sun in 2019. This discovery sparked people's interest in the characteristics, prompting them to wonder where the switchbacks came from and how they form and evolve. Were they fashioned by a process that bent magnetic fields in the solar atmosphere, or were they created on the Sun's surface? Based on the most recent evidence, the switchbacks appear to begin near the Sun's surface. The Parker Solar Probe data was used to trace switchbacks' magnetic zigzag formations back to the solar surface and the solar wind. Between supergranule-like convection cell structures, magnetic funnels develop from the photosphere at the surface. Switchbacks from inside the funnels, rising into the corona and being pushed out by the solar wind. Scientists are keeping a close check on the Parker Solar Probe as it approaches the Sun closer and closer each day now that they know what to look for. We are looking forward to learning more about the mission as it approaches completion in the coming years.